Hey, geometry students. In this lesson, we are going to be talking about dilations. A dilation is a non isometric transformation that changes the size of a figure but not the shape. Remember, isometric means that the dilation didn't change the size or the shape, it just changed like the orientation or the position. A dilation actually does change the size of the figure while maintaining the same shape. A dilation actually maps to a similar figure. Okay, so when we complete a dilation, the original image or pre-image and the image should be similar figures to one another. The scale factor is an important part of a dilation, and any dilation is going to call for some kind of a scale factor. The scale factor is the multiplier used on each dimension of a figure to change it to a similar figure. For example, we'll have a scale factor of 2 or 3 or 5 or 1/2 or 1/3. And then all of the sides of the figure are going to end up being multiplied by that scale factor in a specific way. A reduction or contraction occurs when our scale factor is less than 1. It's a dilation that results in an image smaller than the pre-image. An enlargement or expansion results from a scale factor greater than 1, like 2 or 3. It results in a larger image compared to the pre-image. And then finally, the center of the dilation is the other important thing to know. So for any dilation, you need a scale factor and you need a center of dilation where you're going to be calculating your dilation from. Very technically, or maybe practically, I don't know, the center of dilation can be found by finding the intersection of the lines that connect each point of the image with the corresponding point in the pre-image. So, for example, if we dilate a rectangle and we connect each vertex on the image with the corresponding vertex on the pre-image, all of those lines are going to intersect at a single point, and we call that point the center of the dilation. I'll give you a look at dilation notation here. This is dilation notation. Capital D means we're dilating. The number that follows is the center of dilation. In this case, we're dilating from the origin. If you ever see an O there, that means we're dilating at the origin, and those are the easiest dilations ever if you're dilating from the origin. Okay, you'll learn to appreciate those. K is the scale factor, and if you're dilating at the origin, all you need to do is multiply your scale factor times your X and your scale factor times your y for each of your vertices, and that will correctly dilate the image. All right, now let's get started with some practice problems. Okay, first we need to apply a dilation to triangle QRS using a scale factor of 3 and center C. Now, if I were actually doing this on paper, what I would do is get out a ruler, measure the distance from C to Q. I would use the straight edge to draw a line from C to point Q, and then I would measure how far it would take to make that line 3 times as long. Since I'm doing this on a computer, I can sort of simulate this for a length that's greater than, if 3 instead of 1/3 or something like that, by just taking the same segment and placing it 3 times in a row. So that's going to give me a line that's 3 times as long as the original. And now my new point Q is going to be at this point out here. Okay, so I'm just going to mark that with a circle. This is going to be Q prime out here. And I'm going to do the same thing for S and R to dilate this image. And what you're going to see in the end is a similar triangle. It's just going to be a different size than the original. Okay, so we're going to move this one over so it's a continuation of the same line. You need to make it 3 times as long as the original. There we go. And then I'm just going to put a point there that's close enough. Okay, I'd be able to do this much better if I was using a straight edge. And then lastly, we have this point. So I'm going to draw a line here. This is going to be the longest distance of all from there to there. Okay, copy, paste. Let's just make sure we can move this to the right spot. Copy, paste. This is going to be all the way out here. Okay, so these three vertices make up Q prime, S prime, and R prime of the image, the dilated image of triangle QRS. And then what I would do to finish this off is I would actually just connect these with lines to show that they're connected together. It's going to try to make me snap to points. So again, this would be way easier with a straight edge than it is trying to do it on the computer here. But you can see that I have a similar triangle with a scale factor of 3, and it's been dilated, so it's exactly three times as big as the original. There we go. That is the completed dilation for that problem. One thing I would do if I were making this really complete is make my dilation lines dotted. By the way, did you notice that where the points here connect through the original vertices? So this is R prime, where R prime connects with a segment through R, and then I just continue that line. They're all going to intersect at the same point. That original point they intersect at is the center of dilation. Now, the same thing would apply down here to letter B. Apply a dilation to rectangle JKLM, except in this case, I need to make each of these half of their original length. Now, unfortunately, I have no good way of doing that. There might be a way of doing that in drawings. I'm just going to have to eyeball it here. But if I were actually doing this on paper, I would use a ruler. So here's my 4 original lines. I'm going to redraw, but I'm going to draw lines that are half as long. And again, I just have to eyeball this. I'm not going to be able to do this exactly. If I had a ruler and I was doing this on actual paper, I could do this exactly. So we'll change the image color to red. So here's 1, 2, 3, and we have to do half the way to K. Okay, this one's a little imperfect because I'm not really covering the line, but I'm doing my best. And then this one we're going to go halfway to L. Okay, now when I connect all of these endpoints, I should have a perfect rectangle that's half the length, that's exactly scaled to be half the size as the original. And that is my image of my original rectangle. Okay. Once again, notice that where the lines intersect the image and the pre-image vertices, if I just connect all those lines, they all intersect back at the center point. Next, triangle MNP has vertices M, -2, 1, N, -1, -2, P, -3, -2. Apply a dilation with the center at the origin. Oh, that is music to my ears, because you know what that means? This is the easiest type of problem ever. So for letter C, we need to apply a dilation to these points from the origin. Here's how this is going to work. We're just going to write point M M prime is going to be at, let's see, a scale factor of 3. 3 times -2 is -6. 3 times 1 is 3. And if I were to put this on a graph, I would see that this is a valid dilation that makes it 3 times as big. N prime is going to be -3, -6. And then OP prime is going to be -9, -6. All you have to do is multiply each x and y coordinate by the scale factor, and now I have a triangle that's 3 times as big. Okay, easy peasy. And then lastly, an architect is drawing plans for a building. The drawing for the front of the building is 4 feet long by 2.5 feet high. If the drawing is a reduction by a scale factor of 1/20th, what will the actual dimensions of the front of the building be? Okay, so we took the original length, whatever it is, we multiplied it by 1/20th, and we got 4 by 2.5. All I need to do is undo that dilation, that reduction, and all I'm going to do is multiply each, because they're similar, right? So I just have to multiply each side by the scale factor. But in this case, it's one. I'm gonna have to multiply by 20 to undo the multiplying by 1/20th, right? So I'm gonna have to multiply by 20 to turn it back to its original amount. Because really, what this looks like is x times 1/20th equals 4. 4 times 20 is 80 feet long. Okay, so this is 80 feet long by, and then 2.5 times 20 is 50 feet high. And then here's the thing. This question is going to come up. If the drawing is a reduction by a scale factor of 1/20th, what are the actual dimensions? And then how do the areas of the drawing and the building compare? Well, remember, the area multiplies length times width, but I'm multiplying 1/20th of the length times 1/20th of the width. So instead of it just being 1/20th, it's 1/20th times 1/20th, which is 1 over 400. So the area of the plans is 1/400th the area of the building. It's the scale factor for one dimension times the scale factor for the other dimension. Since they're the same, I just take 1/20th times 1/20th. And that is how you work these problems. Let's just double check that I got those right. 80 by 50, 1/400th. All right, you are ready to work the problems for next time.